Thank you very much for the kind introduction, and thanks for the invitation. It's a pleasure to speak here at ESI and with all of you still here in the late afternoon. Yes, so maybe you noticed that I removed some rigidity part from the title, from the abstract, because I don't have so much time. But if you are interested in this part, just ask me during the week. What I want to present here is a joint work with Matthias Röger from Dortmund, and it's for a geometric variational problem involving a curvature functional. And it's on the topic of the total bending of surfaces that appear in biology. So let me first give you a recap on classical concepts of measuring the total bending. So already 200 years ago in the memoirs of Poisson appeared this energy here on the right, which now in modern language can be written as the Willmore energy, which up to this factor of 1/4 is just the L2 norm, squared L2 norm of the mean curvature vector of a surface S that, okay, for the purpose of this talk, sits in R3. And Poisson proposed this as a model to describe the shape of thin plates. And in particular, so if you take some boundary conditions here, trivial minimizers are minimal surfaces in this class, so if the mean curvature is equal to 0. Here's again the geometric definition in coordinates. So if we have a local parametrization, these are the quantities that are involved in this definition. So we have the surface measure, we have the metric mean curvature, scalar mean curvature, and some unit normal induced in local coordinates. Yes. In particular, let me emphasize once again that here I look at two-dimensional objects. So the surfaces are two-dimensional and in R3 for this talk. Okay. One very important and distinct feature that is very often used in these variational applications is an inequality by Li and Yao, which means that we can control the multiplicity for a surface in R3. I was a bit sloppy to just write S subset R3, but in particular, I want to allow surfaces to touch itself. So the surface can be a potato-shaped surface, or it can also be a surface with a point of higher multiplicity, like this sausage. And my point is that for a certain energy regime, this multiplicity can be excluded by the Willmore energy term. It's very, very crucial in the analysis. Okay, this is a basic model for plates suggested by Poisson already. In the last century, Canham-Helfrich proposed a model for to adapt this energy to describe the shape of vesicles, biological vesicles. For instance, red blood cells or other lipid bilayers that appear in, for example, biological applications. And this energy is now called the Helfrich energy, which instead of the mean curvature measures the defect of the mean curvature to a fixed given number h0. Okay, it's also called spontaneous curvature, and it has been, at least on the numerical level, very successful to describe the shapes that can be found in nature. Okay, there's also two additional constraints that are imposed in the model, usually fixed area and volume. Okay. Here's one of the most important processes in biology in general, maybe. It's the budding transition leading to a division of the cell into two smaller cells. And of course, mitosis is fundamental in this world. So it would be very interesting to understand also such processes in a context of calculus of variations or a biological mathematical shape optimization. And what I want to emphasize in particular is that here in the process of this formation, passing from the one vesicle to two vesicles is that we have a point of higher multiplicity. In particular, it is crucial to also allow for an energy regime where such a point of higher multiplicity is possible, because this is really something that this model has in the real world. Okay, there has been some progress on the variational theory in the past years. I'm, for the sake of time, restricting to the case where the spontaneous curvature is non-zero. Here is again the model, and as usual for a geometric problem, we fix the topology. So S is a closed surface here for me, so no boundary, compact, oriented, of fixed topology. So the topology is then just given by the genus, okay? And among such surfaces with area and volume given, we minimize this Helfrich energy. As opposed to the case of the Wilmore energy, one first important observation is that the multiplicity cannot be controlled. And this is very easy to spot. If you take two spheres, you join them by a thin catenoidal neck, and the radius of the spheres is in the right relation with the spontaneous curvature parameter. This energy will converge to zero if the neck shrinks to zero. So in particular, at this point here, where the neck has become infinitesimally small, there is a multiplicity 2 visible. And this cannot be excluded by the energy itself as opposed to the Wilmore energy. Okay? There's a work around this if you allow for an additional term, but let's say in general, just by the energy, it's not possible. Another very bad feature from the variational perspective is that the energy is not lower semi-continuous with respect to, say, varifold convergence. And this first example goes back to a work of Grosse-Braugmann on constant mean curvature surfaces. And there's also recent work by Christian Scharrer where he did this for compact surfaces. But interestingly, in both these examples, the genus is kind of important. So the genus goes to infinity, both in this non-compact example and in the compact case. So there is no, this phenomenon does not occur for spheres, okay? And even better than in 2020, Andrea Mondino and Christian showed that this energy has a minimizer in the class of so-called spherical bubble trees. So bubble trees of spherical immersions, spherical weak immersions, and in this case, the energy is also shown to be lower semi-continuous. Okay, and in a recent work there, we also looked at the gradient flow of this energy, and if the energy is not too big, excluding multiplicity, we can show a global existence convergence result. Okay, but this is just to give you some background. I want to focus a bit on this third item here, on this bubble tree class, and why I believe it is very good to describe this phenomenon that we see in the mitosis or the budding of biological cells. Okay. So one can easily see, this was already in the picture here, that a sequence of surfaces which are of spherical topology and have uniformly bounded, say, area and Wilmore energy is not compact or not compact, but in the limit process we may find these bubbling phenomena, or also you can find branching points. Yes. Nevertheless, the concept of bubble trees, which is already known from, say, the harmonic map energy of flows, has been formalized in this work by Mondino Rivière in this class of this immersions which are adapted to this Wilmore type energy method. Okay, so we look at immersions in the W22 class now because we have a curvature control. And they proved essentially a compactness or a pre-compactness or a weak compactness result of bubble trees of weak immersions phi I, weak branched immersions phi I, which are defined on the sphere. And I'm a bit sloppy here. I don't want to give you the full, very technical definition, but what you can think of these objects on an intuitive level, they are just a collection of, say, immersed spheres, W22 immersed spheres, and they are glued together at finitely many points. So it's a finite collection of bubbles that are connected by infinitesimally small necks. And each of these bubbles is a weak branched immersion, okay? So weak immersion, I just mean that it's a W22 Lipschitz map from S2 into R3. And if you look at the induced metric, G phi, this is positive definite, at least away from finitely many points where it can become zero. So these are the branch points in this description. And at these points, we cannot really describe the geometry anymore because at these points, the metric is degenerate. But if you look at collections of these weak branched immersions in this class of bubble trees, which then you have to connect them in somehow to fit them into one Lipschitz map, but this is not so. This is very technical and it's not so important. But let's stay with the intuitive picture that is just a collection of these weak branched spherical surfaces. So in this class, Mondino-Scharrer showed existence of minimizers of this Helfrich function. And the picture is kind of reminiscent of what we saw in the experiments for the biological membranes. Now in this work with Matthias, we looked at obstacle conditions. Okay, so we now put an additional confinement constraint in the model. So we put a open set or the closure of an open set omega bar as a container in R3 where everything is going on and our vesicles are trapped inside this container and may not leave it. Okay, for instance, here are some biological justifications if you are interested. For instance, in the blood cells, they may move through a very thin blood artery or vein, I don't know, which is very thin. It can be very thin and it can be, in fact, thinner than the diameter of the cell itself. So it has to deform in order to fit through. And also there has been some experimental work where the impact of the container has been observed. So we have an additional competition of the bending with this confinement now. And this is not a entirely new problem. It has been studied before, starting with the work of Stefan Müller and Matthias from 2014, where they looked at the Wilmore energy, so no spontaneous curvature, and the obstacle given by the unit ball in R3. And they proved, they didn't really prove existence of minimizers at this point, but they proved very sharp estimates on the infimum energy depending on the area parameter. So the area is fixed. And this was then later extended by Wojtowicz. And I would also like to mention the work of Marco, where he looked at the deficit of the Wilmore energy minus a parameter times the area and inside general containers and proved existence and regularity of minimizers for lambda small. Okay. The latest result here by Grunau-Okabe studied the rotational symmetric case, also again with the Wilmore energy, and assumed the smallness of the infimum. In both these latter works, and also in the work of Müller and Röger, the Liao inequality plays a key role to exclude multiplicity and to get the regularity of the minimizer by this exclusion of higher multiplicity form. Okay, here's our new result on the existence of minimizers. So for any non-empty open set, we proved that the Helfrich energy admits a minimizer in the class of bubble trees with prescribed area which are confined by the container. So at this point, we assume nothing on the container. Okay, it's just the closure of an open set which is non-empty. I did not write what the energy of a bubble tree and the area of a bubble tree is, but it's just the sum of the energies and the areas of the respective bubbles, which that are finitely many. So this is the existence result, and it's very much based on this bubble tree compactness theory that was developed by Mondino-Riviere and then later used by Andrea and Christian to have the existence of minimizers without the obstacle condition. In particular, the continuity of the linear term in the mean curvature of the Helfrich energy was a key observation there. Okay, to apply this compactness result, we need to bound the Willmore energy along a minimizing sequence, but this is very easy by just estimating the square, essentially. So adding and subtracting the H0 term, and then you get that the Willmore is bounded by the area and the energy itself. And this gives various things. For instance, it controls the number of bubbles a priori, okay, because each, the Willmore energy is always bigger than 4 pi. This follows from the Liao inequality as well. And in particular, the number of bubbles is a priori a finite number, and also this inequality, together with an estimate of Lee-Simon, gives a control on the diameter along the minimizing sequence. And this is enough to apply this compactness theory of Mondino-Riviere. And the last thing is to check that the confinement condition passes to the limit, but this is not very difficult to see, essentially because we have a compact embedding in 2 dimensions of the W22 space in the uniform topology. Okay. And that means that also this red condition, the confinement condition, will pass to the limit along a minimizing sequence, and this allows us to conclude existence of minimizers. But this was not so difficult at this point. So really the interesting thing, also given the fact that this is an obstacle problem, is to investigate the boundary of the minimizer. Okay, especially at the branch points where the geometry degenerates, if you want, and near the contact set where the surface touches the obstacle. Okay. Also, as a comment, we could also include a volume constraint in consistency with the classical Helfrich model, but it's not needed for compactness. So for the existence part, we ignore it. Okay. Good. So for proving regularity, our approach, because it uses this parametric formulation of the problem, what we would like to do is to use a first order condition to use PDE theory. Okay, but here's already in the classical Willmore energy, without no confinement at all, there's an obstruction. So classically, the Euler-Lagrange equation of the Helfrich functional takes this form. Okay, which maybe looks not so bad. So I write delta here for the Fréchet or Gateau derivative. You could use Fréchet here if you want. So the Fréchet derivative is equal to this term. Let's ignore the terms which come from the spontaneous curvature for the moment. The leading order term is a Laplace. So this is a second order equation in the mean curvature, which makes it a fourth order equation in the parametrization. This is not so much the problematic part. The problem comes from this nonlinear term, which has a cubical nonlinearity. But the space we work in and the natural space we get boundedness only allows us to control L2 integrability of the curvature. But here there's an L3 integral appearing. So there's a priori, it's not so clear what we can do. But this problem already appears in the Willmore, and fortunately, it has been solved in some sense by the seminal work of Riviere, who observed that in conformal coordinates, we can parameterize such an immersion over the disk. Okay, conformal means that the metric then has a diagonal structure. And then this Euler-Lagrange equation here, this formal Euler-Lagrange equation, is equivalent to this now vectorial equation. Okay, so H I use for the mean curvature vector now. And okay, we have a distributional divergence on the outside. We have a gradient, and the gradient is now a flat Euclidean gradient. So there's all in flat coordinates now. So this is a gradient of a L2 function. There's no problem to give this a distributional meaning. And also this red term, which corresponds to the red term up here, now is a product of an L2 function with an L2 function. So it's an L1 function, which is still bad for regularity. Okay, I give you that. But at least we have a distributional interpretation. And of course, it's a geometric equation, so you hope it's not only L1, and this was also used by Rivière to then conclude regularity. And we essentially follow the same strategy in the presence of the obstacle problem now. But it's an obstacle problem. I spoke about the PDE, but how do we get the PDE? Okay, because it's an obstacle condition, we have a constraint on the area, so it's not clear, we cannot vary freely, okay, to get the Euler-Lagrange equation. So if we could vary for any W in, say, C infinity, then we would conclude that this, by minimality, this derivative is 0 for any W, and this would give us the Euler-Lagrange equation. But we need to ensure that any such perturbation is admissible for small t in the sense that we are still a branched immersion, the area is still the same one, and that we remain in the confinement zone. Okay. And all of these things are not immediate to check, but let me quickly go over how we do that. So the branch points are only finitely many. So what we do is we just look at W's which are supported away from the branch points first, and then we will discuss what happens at the branch points. Okay, they are only finitely many. So what is expected is that at the branch points we only get the distribution which is supported in finitely many points, and this is well classified how they may look like. They are Dirac distributions or derivatives of Dirac distributions. The second one, okay, it's a constraint. If the constraint does not degenerate, we can use like implicit function to fix the area correction. And the third one is maybe a bit more interesting, and I will quickly show you how we can do a correction of higher order to stay within the confinement zone in this case. Okay, so for the moment, let's assume also that the container is smooth, that the constraint is non-degenerate. So in the pre-image of the interior of the container, we have non-zero, not constantly equal to zero mean curvature, such that inside we are not a minimal surface. And also that we have no branch points, just to simplify things. Then we can find a smooth function U such that this inner product is positive, and then we make the ansatz of perturbations of this type. W is the direction we are actually interested in, and the U we use as a correction term. Okay. Now, if W does not touch the obstacle, so maybe let me draw a picture here. Okay, there's space. So let's say W, let's say omega is here, okay, and this is the complement of omega. And here from the left, I have my picture of my immersion, phi of S2 or phi I of S2. This gives me some surface, yes, which may touch the boundary or may not touch the boundary. This is the situation. Now in the first case, I'm looking at a neighborhood here where I can vary freely in the W direction. So if W is supported here, I don't need to take the obstacle into account. The only thing I need to do is to fix the area, but this is essentially the implicit function theorem argument that I was hinting at. So this is using that the mean curvature in the interior is non-vanishing. Okay. The second thing is, if we were here at the boundary, we can look at a specific form, namely we can look at those variations W which here point in the interior. Okay, then they are admissible, right? And my ansatz here is to write them as W is some positive function psi, and then I take n composed with phi. Now n is the interior normal of omega. Okay, this is a smooth function, so I can use it. But what I would really like to use in a classical obstacle ansatz would be rather the Gauss map of phi. Okay. But if I replace this here with the Gauss map of phi, I don't have the right regularity because this is just W12 if phi was in W22. So I cannot use this, but I will justify, it will be justified a posteriori while this is good. Okay. If we have this, then we can only perturb in positive t direction. We get a variational inequality now for these Gateau derivatives. So then by the Ries-Radon representation theorem, this can be represented against the measure. The third case is a bit more involved. Maybe if we have a field W which is tangential now at this boundary, so which now points here in the tangential direction, then we cannot use this perturbation, but you can check that if you do a higher order correction, t squared in the interior, so t squared times the normal in the interior, pushing everything in a higher order way inside, then this will still satisfy the confinement constraint. Okay. Yes, and of course this does not give a contribution if we take the derivative, because t squared has derivative 0. So in the end, by the Ries representation theorem, this is the equation we get. Branch points give Diracs or derivatives of Diracs. Then you can check by some scaling behavior that there's no derivatives of Diracs, so there's only Diracs appearing. And this is the equation. And we also proved that any solution of this equation is in this optimal Sobolev regularity. W3p with normal in W2p for all p less than 2. Okay. In particular, we are C1 alpha, and the normal is C alpha. So a posteriori, it's justified that we used here n composed with phi instead of nu composed with phi in the testing. And as I said, this is optimal. You can check that the so-called inverted catenoid, which is well known in the Willmore immersion world, is not in W3-2 with p equals 2, but satisfies the equation with a delta distribution on the right-hand side. Okay, of course, this result applies to the minimizers we constructed by the bubble tree compactness result, but it also applies to many other works. So first of all, in our setting, in our existence setting, we have this dichotomy statement. We either have the W3p regularity if the constraint does not degenerate, but if the constraint degenerates, then we are a minimal surface inside, and on the intersection with the container, the mean curvature is almost everywhere equal to the mean curvature of the container. So the mean curvature is infinity, and you get W2p regularity for all p. But because it's only relying on the Euler-Lagrange equation, our result also has some non-trivial consequences and new conclusions on other variational problems. For instance, the minimizers constructed by Mondino-Scharrer, but also minimizers in the boundary value problem discussed by Dalio, Palmorella, Rivière, and also the Willmore surfaces, so weak Willmore immersions, weak critical points of the Willmore energy, studied by Kuval-Chetzler and Bernard Rivière. And in particular, this applies throughout the branch points. So our result gives us that we have W3p regularity of these minimizers or critical points throughout the branch points. Because the branch points only generate the delta, but we already had the measure term on the right-hand side, so it's not making it worse. This is okay. Yes. I think I have to skip and come to the short summary. So I tried to convince you that this bubble tree framework is a good setting to describe this mechanical shape of biological membranes. I also showed you how to get the Euler-Lagrange equation in the presence of a container, and this gives a measure in homogeneity, but still this is enough to get good regularity results throughout the branch points and also at the free boundary. Okay. Then I would like to finish here. Thank you very much.